Welcome to the podcast of It Doesn't Matter. Today we have Brent Doherty here. You know, our schedule's arranged. We had Block 7 free. I've known him from English class last year, and he's a very successful physicist thus far. So, Brent, do you want to get a doctorate in physics when you're older? Or?
Yeah, I'm thinking about maybe getting a PhD or a master's. Right now I'm looking at some schools that are, great for physics. And depending on where I go and what I want to major in, I might want to get a PhD. A lot of the physics fields I want to go into, like plasma physics, they're kind of requiring PhDs for you to be a staff researcher at different labs.
So when did physics start in your life where you realized you wanted to be a physicist?
Yeah. When I was little, I was always pretty good at math. And then I really like YouTube, and when I was little I used to watch so much YouTube, and slowly I started finding these interesting and niche physics videos online, and they were kind of mixed with math and physics, and it just showed me how the world worked around me, and I became really interested, and it also supplemented that I was good at it. So I don't know, it just became an interest over time, and I started to learn about it more and more. Not even at school, but just by myself, self-studying, and then I slowly developed different connections that I could work with outside of school to develop my interest.
So you mentioned the YouTube videos, right?
Yeah.
I've watched a couple physics YouTube videos, and they're very some of them are about black holes, multi-universal theory or whatever.
Yeah.
What video is kind of true that's freaky for us as a world, something bad that could happen to our world in the physics field or something?
Yeah, I would say in terms of long-term for our planet, we know we're going to collide with the Andromeda galaxy in a couple billion years, and we believe there to be a black hole in that galaxy, which will most likely suck us in, and we don't know the effects of that, but our future human population, if we do last that long, then they'll have to deal with that.
Have mathematicians or physicists, theoretical physicists, have they tried to calculate what it would be if we did get sucked into a black hole? It's quite bleak, I would imagine, right?
Yeah, the whole study that Einstein did was on general relativity and perspective, and what we would experience. Yeah, that's a lot of what Stephen Hawking did, right? If you go into a black hole, you will experience it, but a person looking from outside will see you slowly approach it, but you'll start going slower and slower into the horizon, but you'll never see the person actually enter because all the light is basically getting sucked in. But truthfully, I don't think we'd know right now what exactly would happen if an object went into it. But we know generally different energy conservations and behaviors that happen with black holes. But something so tangible like that, I don't know if we're sure with our current technology.
All right, you mentioned guys like Einstein and Stephen Hawking. When it comes to in high school, right now, I imagine you're working on calculus and physics. Does that stuff really translate to when you get to the level of Hawking and Einstein, where they're just pure theory of what's going to happen right now? Do they use the math that you use now?
Yeah, I would say, I can give you a specific example. In any physics year course, you might come across the equation F equals ma, force equals mass times acceleration, and a lot of the time, you'll see this in different forms throughout physics. The Einstein field equations, which are notorious for being difficult and crazy looking because they have these sort of tensor and matrix components in them. But if you simplify it to its bare bones, it's actually just a representation of F equals ma, the simple equation that you learn in first year introductory physics. And I think that's one interesting thing, but you're mostly just applying higher level mathematics to a simple thing and then extrapolating data from that. That's what I would say.
So, like when you did your paper,
Yeah.
you used math, right?
Yeah. I preface it in the introduction and in the beginning of the paper that we see certain observations with telescopes called the EHT and the SG, which are different telescopes and different black holes. And you'll find that there's predictions and certain observations with like the geometry of space-time around black holes. And from there, you can kind of form theories. I worked with a professor on my paper on an alternate theory to black holes called dynamical gravastars, or gravitational vacuum stars, where you're basically trying to evade a singularity that comes with a black hole. If you talk more about black holes, you'll find that in the center of them, we predict there to be a singularity, which is not mathematically possible. And so the theory that we're working on is basically evading that. And a lot of it can come down to seeing an observation, making a theory. In this case, I don't think it was so much up to the data, because the paper I did was more theoretical. It wasn't observation-based. We didn't really, the only numbers we used generally from other studies was something called like the Schwarzschild radius, which is kind of the mass or radius of a black hole, or Schwarzschild mass, which is kind of like a predicted geometry of a black hole. Generally, when we talk, I think a big thing in math and physics is paradoxes. You know, we call things paradoxes, but the underlying issue with paradoxes is a paradox doesn't exist within itself. It's our lack of understanding of something. We know it not to be true. We know there to be a reason for something.
So is the singularity a paradox is what you're saying? We know it not to be true?
Yeah, we're perceived, like, it's imperceivable that you get all this mass crushed up into a single space, and because it doesn't follow a lot of laws that we see, right? It's a paradox. It doesn't follow the behavior that we usually see. And so we know it not to be true generally, unless there's some external factor that we don't know just yet, and some law we don't know. But we know it not to be true, and we can explore and make different models that try to evade, that either try to evade that theory or that observation, or just try to work around it, basically.
So what did you guys do to work around the theory of the singularity?
Yeah, so black holes can be modeled, in our case, there's a couple equations called the Tolman-Oppenheimer-Volkoff equations, or for short, TOV equations. They model relativistic gas, which is gas or a star. It's relativistic gas or a star, which is basically under effect of the theory of general relativity, and which is how space-time is curved and how it's affected by energy and energy conservation. So we use these equations to model and make a structure within a mathematical program. I use Mathematica, so we have this long notebook with a bunch of systems of equations, these complex system of equations, which sometimes we may have to integrate or solve by hand, put in, and from the system of equations, we can extrapolate graphs, and we can model graphs, and this gives us information about the behavior of the black hole, or behavior of the model of our black hole, and see when it works, when it doesn't work, when the model fails to evade the singularity, what mass and what energy densities you need to have a proper structure for this black hole.
What's the most important thing that you found out from this paper, that you cherish from the paper that you found out about black holes?
My paper was important because it modeled when our black hole structure didn't work and when it worked. So there's, say, this graph, right? And there's a line that basically goes, shoot. It's kind of like a diagonal line. Yeah. And on one side of this line, you're getting the region where it doesn't work. So the two axes are like energy density and mass, which are basically components of a black hole. The density of energy, mass, and sometimes pressure. And so for certain energy densities and mass, it doesn't work, and for some it does. And that's kind of what the final figure looked like for our paper. But there's still more studying to be done.
Physics probably, what I'd say is probably one of the most important fields when you look at, like right now. I mean, black holes are definitely like the wonder of the universe.
A black hole is a star, right? And it's a collapsed star, and it has a certain amount of mass, pressure, and energy density, which allows it to just keep collapsing on itself. And the gravitational force that comes with so much mass in one space sucks in matter from around it. And it's hard to explain. It's hard to explain intuitively because it goes into this finite point, which we think. But yeah,
It's mad.
it's hard to explain, I feel.
Is there one kind of close to us?
I would say the one that I explained to you with the Andromeda galaxy is probably the closest one we know of. But it doesn't pose as a scare right now because
It's 2 billion years.
it's like billions of years away. And yeah, it doesn't really pose a threat right now. And as a person, it's like it's hard to say that our civilization could last for another 2 billion years. I have no clue.
Yeah.
So it's not a worry right now. I would be more worried about things we would do to ourselves rather than black holes. The other research I'm doing is in fusion energy and the use of you basically combining atoms to get energy.
Yeah, so I had a question about that. So my friend, his dad is a pretty successful physicist, and he went to Saudi Arabia, and he pitched to the Saudi Arabians. He was like, it was at Princeton. We have, I don't know, I mean, you'll tell me how far it's gone with nuclear energy, but they have this blueprint, right, of how they could get energy.
Yeah.
And the Saudi Arabians did not want to spend money on it. Like,
Yeah.
it shouldn't be a surefire thing for like barons of oil to invest in. Because do you think nuclear energy will take over?
Yeah.
Yeah.
I was actually thinking like the English class I was with you last year, my independent research project was not on the physics of fusion energy, but it was more on the implications of society and why we're not investing right now.
Yeah.
So the reason we're not investing is because fusion energy, well, first of all, a lot of the Saudi Arabian income is from oil reserves, right?
Yeah.
And it would be counterintuitive to them because they're not going to make
Yeah,
money
and
from...
how powerful is nuclear energy compared to like a power plant of oil? Like,
yeah, there are specific like ratios into how nuclear energy has a lot more potential than traditional fossil fuels because you're getting so much energy from such a small thing. You combine two atoms, you get a neutron which holds a bunch of energy, and you can insert that energy back into the system and keep resupplying it until you get this ignition, we call it, of the plasma, and it keeps going. And generally we're trying to model the structure of a star, which, as we know, is super powerful. I mean, that's the most efficient energy producer in the universe, right next to the direct transformation of matter into energy, which we don't think is possible. Then there's fusion energy. It's the thing that's right behind it. And that's why all the stars go through that process, because it's the most efficient form of energy production.
And how does it like work day-to-day basis? You have obviously the reactors, which you talked about in your paper, right, last year?
Yeah. A lot of the troubles with implementing fusion energy is that you have this huge reactor. It's not huge, but the size of a building, basically. You're trying to set off one ignition to get like a surge of power. The thing we're trying to implement is this kind of constant stream of energy to keep it going for a long time, to make it less of a reactor and more of a energy production machine. So that's what we're currently working on implementing.
And like, would there be generators? Would there be car? Would you consider it an engine if it had fusion energy? Would there be that on the like small level? Would you have nuclear energy within your home or within your car, or would it only be in these reactors? You said, or
yeah, the challenge with making a small scale is that you have to have these huge complex magnets that are super powerful to get the machine to compress the plasma and hold it in place. And the problem with that was first of all, it would affect other systems. Also, if a plasma reactor failed in your car, it would basically send a jet stream of 100 million degree hydrogen through the car, making like a hole, like I don't know how big it would be, but it would just melt everything.
I hear about nuclear energy all the time. How does that energy transfer to life in the simplest way, would you say?
Yeah, a lot of the reactors, like current reactors with fission reactors, which do the opposite thing, you're creating heat, which evaporates water, and then the water spins turbines. And so generally, we would continuously want to insert hydrogen into a fusion reactor. The process keeps going, it keeps perpetuating itself, and with the only addition being the fuel.
Yeah.
And that would heat up something else, like a water, into water vapor, which would spin a turbine, which would create energy. There could be more efficient ways of doing it.
And then we just generate energy that way.
Yes, yeah. And you produce electricity from the turbine.
So and the oil industry is massive. I think it's probably like, the biggest financial industry right now, one of the biggest?
Yeah, it's one of the biggest, but I think within the next hundreds of years, it's probably going to die down as we start to lose oil reserves.
And what's going to happen, like, like Manchester City football team, like the owners of oil baron, you got Saudi Arabia, like making game-changing acts. If they're not investing in nuclear energy now, is that whole empire of oil just going to die down in a new wave of barons?
I think it could, in the fact that you're running out of your biggest income source, and you're not investing into the future. I think, Jenna, I also wrote about that. When these fuel sources run out, you're going to get a lot more incentive to dump your budget into these fuel sources.
Okay. Yeah.
Because as of now, there's no use in doing it because it's just research development. There's no profitability. And yeah, I mean, it's an interesting thought to what will happen to people who kind of stick with fossil fuels. And I think for the most part, as they get increasingly rarer because we run out the supply, a shift will happen into nuclear energy because it's more incentivized, because there's more of a need for it.
So like, when you see the climate change initiative, like you're not happy. Are you happy with like the way it's going socially with publicity? Because I don't think a lot of people like know about nuclear energy and all that,
I would say there's a discrepancy between what needs to be done and what's happening right now. There are certain activist groups which I do like. I mean, people that we make the issues at hand and what's being degraded aware. We make that aware to people a lot, like with dying coral reefs, whatever it is, the effects. But our changes are not as publicized. I think fusion energy and different strategies in which we can actually implement into our society, like different energy sources, different ways of regulating the carbon cycle, whatever it may be. I don't think that's publicized, to your point. Yes, I wish it would be more, because I think it can be a huge component to how we can save our planet's climate change crisis.
Yeah, I didn't know that much about nuclear energy, so That's right. Black holes, I thought they were much more mysterious, but it seems like that our lifespan is so short that it's more for fun that we just like to research it almost.
Yeah, I think in the future potentially. I mean, we kind of have to research it as it's gonna, it's something to research. I mean, because we know it has such a potential for what we could use it for. We could potentially use the technology of black holes, the science of black holes, to harness something that we could use, say an engine, or it's kind of a utilitarian way of looking at it, but we may be able to use the physics and science behind black holes to our advantage.
Oh, because it's a star form, and that's the cleanest, best way. Wow, so it's all interlinked almost.
It is interlinked. I mean, that's why, a lot of this stuff even is one field. Black holes and plasma physics are connected in a way because it's all astrophysics, and a lot of the things in astrophysics are connected through stars and through how our universe expands, different things like that, the evolution of our universe, which is all interconnected in a way.
Well, it was a pleasure having you on the show.
Of course.
Very, very high intellect of physics, and I hope that wherever you may end up, that you just keep working on the energy.
Yeah, hopefully we get a working reactor soon.
That'd be crazy.
Yeah.
Especially if you're one of the ones to create and breaks news.
I would love to.
Definitely, yeah. That'd be crazy. All right. I think we're done, and that's the first episode of It Doesn't Matter.